So what we've done so far in this class is we looked at systems of equations, and then we realized that a way to solve systems of equations is to use these matrices. And then, so we just practice with that a little bit. And basically, when you do these row operations in the matrix, that's the same as just doing the same operations on the equations. It's just that you eliminate the variables when you focus on just the matrix. Now what we're going to do is we're going to study the mathematics of matrices, just as a separate issue. And eventually we'll bring the two concepts back together again and say, you know, how do matrices, after we've studied them mathematically, how does that relate back to systems of equations? So you want to think of what we're doing right now as a little bit of a detour from where we've been, but we will come back around and make a connection. So we'll start off with a little example here. It's not much of an example, but we just want to have a couple matrices up there to work with. So here's a standard matrix. I try to keep the numbers 1, 2, 3, 4, 5, 6 whenever I can, just so it's easy for you to copy them. You know, you can just glance at it and know what it is. And here's another one here, 1, 2, 3, 4, 5, 6, but it's in a different configuration. So last time we learned about how we identify these matrices in terms of dimensions. And it's really just about the rows and the columns. So this guy here, this is row 1, and this is row 2. We're just doing the anatomy of a matrix. We want to go in and see where all the structures fit together. And this is row 1, row 2, row 3. And then we have our columns. Okay, so we have 3 different columns here. These are columns 1, 2, and 3. And then over here I have column 1 and then column 2. So even though A and B have the same entries, you might say they're like each other in the sense that they both have 1, 2, 3, 4, 5, 6 in them, but they're very different matrices in terms of their dimensions. This guy, A, is well, it's 2 by 3. And this guy, B, is a 3 by 2. It's got 3 rows and 2 columns. You do the rows and then the columns. That's just the convention that we've adopted. So even though they have the same entries, they're different matrices, and we can say it's obvious. You got to be careful when you say it's obvious in a math class, because it's not always obvious to everybody. But in this case, I think it's obvious these matrices are not the same, because this guy's more of a flat rectangle and this is a vertical rectangle. They don't even match up, right? So it's obvious. That's why I say it's obvious that A is not equal to B. Okay, so in this example, that's clear, but now we want to make mathematically accurate exactly what it means for two matrices to be equal or not equal. So we're going to say matrices are equal you got to have two things. One, they have to have the same order. So the rectangle has to be the same as the other rectangle. They have to match up. Okay, so if you have different rectangles, they're just not going to be equal, just like that case. But when you do have the same rectangles, then you have the additional thing that they have to have the same exact entries as well. So we'll just write that down. They have the same order. That was the word we used for those dimensions there, the 2 by 3. That's the order of A, and the order of B is 3 by 2. So they have to have the same order. And then entries are equal. Now, how can we say that? That's how you'd say it in English. The entries are equal. But I want to be more specific, because you might think, well, those have equal entries, but they have to be in the exact same location. So mathematically, the way we can describe that is we can say Aij is equal to Bij. That just says that the entry in the ith row in the jth column is the same as the entry is in the ith row in the jth column. So for here, we could say A is an m by n, and B is also an m by n. That's what it means for them to have the same order. And then what it means for their entries to be the same is that we can use these subscripts. So again, this is what you need in order to solve problems. You just need the intuition to be able to do it. But as we're doing that, what we want to try to do is gain some mathematical maturity. And so if you can, try to understand why it is that that notation means this statement in English. Try to do that. And if you don't feel like doing it, it's okay. At least just understand that they have to be equal. Okay, let's have a little example where that might get used. So here's a little problem similar to one in the book. Maybe I put something like this on the midterm too. So this is a way to incorporate this new concept of matrices with the systems of equations that we've been doing before. If I have 3 minus x and 3, z minus x, y plus z. So that's a matrix, but it's got variables in the entries now. And you want to think of this as, if it helps you, make a little grid there. I'm thinking of this as a 2 by 2 matrix. And then I'm saying that that matrix is equal to this matrix, x or y, x plus z, negative 1, 2. And then the command would be solve for x, y, and z. So this is just a way of disguising a system of equations. It's linear. This is a linear system of equations. Why is it? Why do I say linear? Just because I see only powers of 1. I can attach that word linear to any time I see the variables only having powers of 1. Okay, well, what can we extract from here? I want to find out what the variables are, and there's basically 4 equations. I've got x plus z equals 3. I've got z minus x is negative 1. And if you just pause for a second and look at it, you can notice that you have 2 equations here that involve x and z and a number. So then let's just focus on that, and then maybe we can just get those 2 variables. So the first thing I see here is I have z minus x equals negative 1. That's from here and here. And then I also have x plus z equals 3. And we don't have to go back and use our matrix method to do these. We can just do this the old-fashioned way like you would in high school. If I were to add those 2, I get 2z equals 2. So then that tells me that z equals 1. And then because I know that z equals 1, I can go back and find out what x is. So x plus z equals 3. That implies that x plus 1 equals 3, which tells me that x equals 2. So I've got 2 of them. And then I've got a couple more equations to work with, actually. I've got 3 minus x equals y. I could use that because I know what x is. Or I could use y plus z equals 2, and I can find out what y is because I know what z is now. So let's just use, let's say we'll use this equation. I must have y plus z equals 2. But then that implies y plus 1 equals 2. And so now I have y equals 1. So my solution is x equals 2, y equals 1, and z equals 1. Now this is actually an overdetermined system because I have 4 equations. I didn't even write down the 4th equation. That kind of shows the overdeterminedness of it. So this is an example of an overdetermined where you actually do get a solution, but you don't usually for overdetermined. Because I have 4 equations and only 3 variables. That's what I mean by overdetermined. I want to get used to writing these answers in a matrix, because after all, a matrix is a way to think of it is it's a vessel of information. It's a box, but each little entry is information. So here I've got information, so we could write it this way. Remember last time we talked about column vectors and row vectors, so I can organize my variables in a matrix. That's a 3 by 1 matrix, but we call that a column vector. We don't call it a matrix. We have a special name for these guys. And then I can say that if that's the column vector x, y, z, then that must be equal to 2, 1, 1. You can just organize your information that way in a matrix. Next, we're going to start talking about special matrices. I have to introduce you to the world of matrices. I have to show you there's some special ones, and then of course if they're special we're going to have names attached to them, so then when I refer to those names you're going to need to have an image pop into your mind of those specific matrices. So the first set of special matrices is square matrices. Well, the name implies that we're not dealing with just a general matrix where we have a rectangle, but it's now specific. It's a square matrix. So if I want to say what the order of all square matrices are, in order to get a square, I need to have the rows be the same as the columns. That's the way to think of this, is that you have the same number of rows and columns. So A would be an n by n. We usually use n by n. You'd think maybe we could use m by m because it's, in general, it's an m by n matrix, but that's usually what we call a square matrix, an n by n. Okay, so let's have just a couple simple examples, like 2 by 2. Right, there's a 2 by 2. That's a square matrix. We're going to spend a lot of time with 2 by 2 matrices, because if you think about it, a 2 by 2 matrix is the first square matrix where you can actually get some interesting stuff happening. And so but it's not as complicated as 3 by 3, so we spend a lot of time on these just to learn the world of matrices. I could have a 3 by 3. And here's where I want to introduce for the first time a 1 by 1 matrix. I always like to go back to the simplest, fundamental example if I can. And sometimes when you do that, it becomes ridiculous. But let's take a look at that. What if I have a 1 by 1 matrix? That means if it's 1 by 1, then it's 1 row and 1 column. So that's just one number. So this is a 1 by 1. But you're already familiar with 1 by 1 matrices. In fact, you've dealt with them your whole life. These are just numbers. Okay, so it's ridiculous to add brackets around it. We don't want to add brackets. This is just 5. So 1 by 1 matrices, we don't really write brackets around them. They're just the numbers. That's what 1 by 1 matrices are. But what that is it's an opportunity for you to learn a little bit of abstraction. So you're used to the numbers already, and now we have this new concept, and so what you're doing is you're making a connection between something you learned a long time ago and you're really familiar with the new thing. The new thing being matrices. This is a 1 by 1 matrix. Okay, so those are just basic square matrices. Now within square matrices we have some other special matrices. First one is diagonal matrices. So think about the language there. What would be a diagonal? Why would they be called a diagonal matrix? Even if you can't answer that question, it'll help you remember it if you try to imagine what the answer is before I tell you. Then you imagine it. Okay, you might get it wrong. Then I tell you, but it'll stick then. Right? We're all about just trying to download the information. So any little trick we can do to help that out is valuable. Okay, a diagonal matrix. So first of all, it's going to be a square. So it's within the square matrices. This is not a diagonal matrix. This is not a diagonal matrix, but this is. Okay, so let's see, what would be a diagonal matrix? So let's have some examples here. So if I give you that's a diagonal matrix. So now ask yourself, why would we use the word diagonal? Well, here's the diagonal that I'm talking about. It's not the zeros. It's the one going left to right from top to bottom. And then we could have a larger one. A is 1, 0, 0, 0, 2, 0, 0, 0, 3. That's also a diagonal matrix. And there's the diagonal. And then let's have one, A equals 5. That's a diagonal matrix. It's a ridiculous one. It's not really interesting, but as long as we're looking at it, we might as well look at the most trivial examples. These are all diagonal matrices, and what do they have in common? Stay here. What they all have in common is this. I can say it in English, and then we're going to have to write it down a little bit mathematically. So what's clear here is that I've got stuff that's non-zero on the diagonal and then zeros everywhere else. Okay, and then we're going to have language to describe this. We're going to call this the main diagonal because there is this other diagonal. And then here you might even think maybe that's a diagonal and that's a diagonal. So there are other things that could potentially be called diagonals, but we're talking about only this one here, which is called the main diagonal. Okay, so if I want to describe this in English, they're square with only non-zero entries being on the, and then here's this new vocabulary, the main diagonal. Now I want to emphasize the language here. And math is very precise, and no words are wasted. Okay, so there's something specific here. It says with only non-zero entries being on the main diagonal. So sometimes what you might think, especially when you only look at those two examples or those three examples, you might think that you can't have 0 on the diagonal, but you can. It's just that the only place you have non-zero things is on the diagonal. So let's have one more example. If I have, there's a 4 by 4, I can actually have, see here's the diagonal, I can actually have a 0 on the diagonal. That doesn't make it a non-diagonal matrix. But still, it adheres to the definition that the only non-zero things are on the diagonal. So this is still diagonal. That's going to come up later on because we're going to be making diagonal matrices. You're going to be making them. And sometimes you'll get a 0 there. So I'm just going to kind of cover that so that you don't worry about having a 0 in the main diagonal. All right, now let's just, what I'm creating here is a little Russian doll kind of a thing. So the biggest group is the square matrices. Then within the square matrices, we have these special ones called diagonal matrices. And now within the diagonal matrices, we're going to have some special matrices. And these are called the identity matrices. Now this has special notation. We're going to use I for identity. So I sub n, this is going to be an n by n matrix. So it's square. And here's an example of, well, let's add some stuff here. So it's an n by n matrix, and then it's diagonal. But then it's a special kind of diagonal where you have only ones in the main diagonal. So as some examples, okay, so this is the general one, I sub n. It's an n by n matrix, so let's go down to the basic level. How about I sub 1? Okay, well that's now a 1 by 1 matrix. So that's 1 by 1. That's the stupid example, right? But let's get it out of the way. So it's a 1 by 1 matrix, and it's got to have a 1 in the main diagonal. Every entry in the main so there's only, that is the main diagonal. So there it is. That's the identity, in a 1 by 1 matrix. Now this place, ask yourself, okay, is 1 special in the number world? Is it special? What's special about it? Well, okay, let me help you. If I take 2 and I multiply it by 1, I get 2 back, right? And if I take 5 and I multiply by 1, I get 5 back. So is there any other number that does that? Where you multiply, I take the number, the mystery number, and I multiply it by something, and I always get back the same thing again. 1 is that unique property. So 1 has the property that 1 times a equals a in the real numbers, or wherever you want to be, integers. So it has this special property. Okay, so we're going to find that that property exists in all of these n by n matrices. So this is now a connection between the original number world that you're so familiar with and this new world of square matrices. So I sub 2, okay, now that's got to be a 2 by 2 matrix. And I've got to have, it's got to be diagonal, so I can't have anything 0 outside the main diagonal, and it's got to have only 1s in the main diagonal. So there you go. There's I sub 2. And then I sub 3. These are the ones we're going to be using, so might as well get those out of the way and write them down. Okay, it's a diagonal matrix. Everything's 0 except the main diagonal, and I only have 1s in the main diagonal. Now, I can't show you that this property is true yet because we don't know how to do matrix multiplication. That's coming in a few minutes. But since I've got this here, I just want to make a connection between your familiar setting, the special case of 1 where 1 times anything equals the anything. It's also true in a matrix. So if I have I sub n a, that's equal to a. And on the other side too, it wouldn't have mattered if I multiplied on the right side by 1, right here. So it's also true that a I sub n is equal to a. And you don't know what matrix multiplication is yet, so this is, I just want to have it consistent here in the notes. Yeah?
So as a more general question, why don't these matrices deal with the additional segmented column that we had earlier when solving systems of equations?
Yeah, well, first of all, we're just dealing with square matrices. In the systems of equations, that little extra column represented the other side of the equal sign.
And so we're not doing any of that?
No, in fact, that's what I was kind of saying at the beginning, is that what we're doing right now is we're removing ourselves from the systems of equations, and we're just studying matrices by themselves, the math behind matrices. So the subject matter would be considered linear algebra, which that was still linear algebra, what we were doing before, but now we're just looking at pure matrices and what we can do with them, the algebra of matrices. Eventually we'll come back and we'll make a connection with those systems of equations. Let's use this one. Okay, so now we're going to do a little abstraction. If you paid attention to the first lecture, I mentioned the goals of this class. One of them is to get mathematical maturity, and so what we do is we abstract. That's a skill that you learn in college in a lot of different subject matters. Okay, so what have I just done here? I've got the whole world of matrices. So that's any matrix you want to think of, rectangular or even square, anything. But then within this world, I've got square matrices. Right, those are just n by n. So here I could have m by n. So it's a bigger world. Within this, the square matrices exist. Then within the square matrices, I've got diagonal. And then within diagonal matrices, I've got identity. This matrices. And a lot of times what we do in mathematics is we say, okay, there's this general thing, and then there's this little subset, and that's interesting. And then even within the subset, there's another subset, and that's interesting. And then even within that little subset, there's... But the thing is that if I can say something is true about this, it's also true about all of these automatically. That's another way of thinking of this nested set. So that's what we've just done. We just identified some special matrices. We started off saying, okay, here's rectangular. Then we said, okay, square, then diagonal, then identity matrices. And you should be familiar with what all of those are for the exam. The next thing is, so that's all section 8.1. This is 8.2. This is matrix operations. What are operations? Why would we use that word? Well, if you remember, when you may or may not, but when you first learn addition and subtraction and multiplication, those are called operations. Those are operations between numbers. But you don't really focus on that word, you just focus on addition and subtraction and multiplication. But the translation for this word is, this is plus, minus, multiplication, and division. Right? Those are the operations that we do in math. So we're going to want to do all those things. We did them so successfully in your early life with 1-by-1 matrices. Now we'd like to do all those things with 2-by-2 matrices, and then 3-by-3, and then 4-by-4. So you're pretty familiar with how to multiply and add and subtract there. But it's a little more complicated when we get to higher dimensions. Okay, so let's start off with addition. We want to take a look at what does it mean to add two matrices? Well, first of all, it only makes sense if A and B have, don't just guess in your mind, what should they have to have? The same order. They got to be the same rectangle. I can't match up rectangles that don't have the same dimension. So they have to have the same order. This you have to have m by n and m by n. So now we're in the general world here. We don't have to be square matrices. We just have to have them match. So for instance, it's easier to just see when it doesn't work. Okay, this doesn't make sense. That's the first thing. They have to match up as rectangles. Okay, so if they do have that, if both A and B are m by n, so if we do have that situation, then what should it be? Well, let's write it down here. So A plus B, okay, that's going to be, here's A, and then here's B. They're going to match up, so I can draw them with similar sizes there. And what should we do? What should be the case? Well, it's going to make a lot of sense if I take the entry here. So what is a random entry in the middle of this matrix? That's going to be A, I sub j, where this is the ith row, and this is the jth column. So I'm just taking any random entry, right? It might be the third row, fifth column, whatever it is. And then what should I do? Well, I should match it up with the corresponding element over here. So this is Bij. And we're going to match those up. So this is going to be a new matrix. This one was m by n. This one was m by n. And the resulting matrix is also going to be m by n. And what should we have in the ith row and the jth column? Well, I should have aij plus bij. I'll write it down here. Okay, so that's how I describe it mathematically. It's not that hard, but what it is it's an opportunity to practice with notation so you get used to it. So let's have an example where we can just see. You don't need many examples of this. It's intuitively straightforward. In fact, I usually kid that if I came up to you on the street and I go, stick 'em up, okay, tell me what the answer to this is. Well, what else would you do? I mean, even if you didn't know anything, you got to save your life, right? So you got to guess. So I think I would guess, well, I'll just match those up and hope, right? Just match them up. So that's what this all says. It just says match the entries and add them like you would if they were 1 by 1s or just numbers. So 7 plus 3 is 10, and then -5 and -2 is -7. 1 and 1 is 2, 0 and 4 is 4, 1 and 2, 3, and then 0 and 4 is 4 again. So it's the obvious thing. There's nothing else you could think of to do. Now in the matrix world, we have two kinds of multiplication. We have multiplication of matrices, and then we also have what's called scalar multiplication. We'll start with scalar multiplication, and it's also called factoring. So think about what the word scalar is. Scale, how about a scale model? What is a scale model? If I have the city of New York and I want to make a scale model of it, then I'm going to take every dimension of every building and every street and I'm just going to multiply it by 1 over 10,000 or something, right? And then scale everything down and then build my little model. So you multiply everything. That's what scaling is. You multiply everything you see by the same value. That's why we use this language here, scalar. Okay, so what's an example of that? If I have CA, now notice the notation here. I'm using a small c. This indicates that we're talking about a real number here. And then A is a matrix, say an n by n or m by n. We can have anything here. Okay, so then what is this? It's C. We can write down let's write down every n by n matrix in the universe. Here they are. The first entry is A11. Then I go all the way down. This is the first row, first column. This is the first row, the nth column. Then I have the mth row, all the way down the mth row, first column, and then mth row, n column. So I can write that down. Not too bad. And then, so what should this be? If we use the word scalar, and we have scale models, and that means multiply everything by the same number, then this should be the matrix CA11, CA1N, CAM1, CAMN. So I just did the scalar multiplication of every matrix in the universe, right there. They're all done. So that's what's nice about math, is we get these general formulas, and then we can start to do some specific examples. So the specific example is if I have 5 times 1, 2, 3, 4, well, that's just 5, 10, 15, 20. I just scaled it up, scaled everything. And then similarly, I want to add to the board here, if I have, let's do another example. If I have 9, 12, 6, negative 3, you see, you can notice that every single term has a 3 in it. So then you could factor out the 3. That's why when I put it all the way up, you'll see it. But so here I see there's a 3 in everything. So let's factor that out, put the 3 outside, and then I have 3, 4, 2, negative 1. So that's the opposite direction, factoring. So that's scalar multiplication. Now we need to get into how do you actually multiply two matrices. We'll do this by example. Just watch me do one, and then we'll try to extract out or tease out some of the method that we used, and we'll try to make a generalization of that. So let's start off with A, B. So it's two matrix multiplication, or two matrices multiplied by each other. The first one is 2, 1, negative 1, 3. And the second one is 1, 2, 4, negative 1. Now, if we play that same game where I say, stick them up, tell me what the answer is, then your intuition would be, well, I'm just going to go 2 times 1, and then 1 times 2, and then negative 1 times 4, and 3 times negative 1. And you would not live past that encounter, because it's wrong. Okay, so the intuition doesn't work here. Now, what we'll discover later is that what we're trying to do with this matrix multiplication is we're trying to preserve some stuff that's inside these matrices, and we haven't talked about them yet, but there's geometry inside these matrices. There's a hidden picture for each of these matrices. And when we multiply them, we're trying to preserve that geometry. And when you don't know what the geometry is, it's hard to imagine it, and I'm not going to spend any time with it yet because I want to do the matrix multiplication. But that's why we have this funny kind of matrix multiplication, is to preserve this stuff that's going on behind the scenes, and we'll learn about that later. Okay, so how are we going to do this? Well, first of all, I'm going to tell you, I got to tell you what type of matrix you're going to get back. So I'm going to multiply these two, and we're going to get another matrix. But even right now, if I said what kind of a matrix would you get, you wouldn't know unless I tell you, or unless you've had some experience. So I'm telling you right now, when you take a 2 by 2 matrix and you take another 2 by 2 matrix, you get a 2 by 2 matrix. And we're going to have to learn, all the particulars of that, but we'll just do one example. Now, if this is going to be a 2 by 2 matrix, which I'm telling you it is, then it's going to have entries. Here's the first entry, C, first row, first column, first row, second column, second row, first column, second row, second column. So those are the entries. Now I have to tell you, how do I get each one of those entries? I think I'll start with a clean board for this. All right, so for the first one here, I'm going to just show you a picture. Let me make it a little smaller. So this is going to be C11. This is how we obtain C11. So now think about it. We've got this notation here, and this is mathematics. We've got C11. That's going to mean something. It's not going to be just random numbers there. So the way I obtain the element that goes in the first row in the first column is by combining the first row here and the first column there. I'm going to combine those two things, and that's going to create a 1, 1 entry. So let's put that up here. That's how I create C11. And what I'm going to do is I'm going to take the 1, 4 here and turn it on its side. I'm going to match those up like this. So if you put the 1, 4 here, I'm now going to do 1 times 2 plus 4 times 1. That's how I match those up. Now, if you've ever seen dot product or something in a physics class or something like that, maybe in high school or something you saw dot product. That's what we're doing here. We're just doing the dot product between these. But the book doesn't call it dot product. Just mentioning that in case you've seen it before. Okay, so C11 is going to be, it's 1 times 2 plus 4 times 1. So that gives me 6. That'll be the first entry. So I just told you how we do C11. C21 is going to be the second row with the first column. So it'll be the second row matched up with the first column, and then we're going to do that same thing that we just did. So I'm going to, here I can write these in, it might help. I have a 1, 4 there, and a negative 1, 3. This one was 1, 4. So when I do this same multiplication and I turn it on its side and match them up here, 1, 4, now I'm going to have 1. Instead, it's going to be 1 times negative 1. And then I'm going to have 4 times 3. So that gives me 11. That's the next entry. We have 2 more to do. All right, well now let's do C12. That's going to correspond to the first row, second column. So that'll be the first row here, that's 2, 1, and then the second column is 2, negative 1. Now let's do the same thing. We're going to take this mentally. When I say turn it on its side, that's what you do in your mind. You can just match them up like that. So now I have 2 times 2 plus negative 1 times 1. So that's 4 minus 1 is 3. And then the last one, C22. Now we kind of established the pattern, so we can go a little more quickly. 2, 2, that's going to be the second row here with the second column. And then here I have negative 1, 3. So take that in your mind and match them up like that. 2 times negative 1 plus negative 1, or positive 1. This is a positive 1 here. Times 3. So that's equal to 1. Okay, so now I can say what AB is. That's going to be 6. And then C21, that's second row, first column, so that's down here. And then C12, that's 3. And then C22 is 1. So that's AB. Yes?
How does that become a positive 1?
Did I write it incorrectly?
It's always been negative 1 times 3 on the C22.
Oh, yeah. Whatever this is, it should be that. Yeah. I wrote it here positive, that's why. Yeah, thanks. Yeah, that's a negative, so this is a negative, so then this is negative. It's negative 2 plus negative 3 is negative 5, so this one's negative 5. Thank you. Yeah, and please do that. When you see a mistake, tell me right away. Don't be afraid to tell me I made a mistake. Because the sooner that we fix it, then the sooner I can move on. Thanks. I do my best to make perfect lectures, but I don't have a long track record of being perfect, so I don't exactly expect it to happen. I still try. So now let's extract out what happened there. Let's get a little bit from this. Ultimately, we'd like to be able to write down in general what it means to multiply two matrices. So from this, maybe we can get that from this one example. All right, so if I have A times B equals C, let's see what had to happen. Notice that what I just did there wouldn't have worked if the columns and the rows didn't match up, right? If they didn't have the same number of elements. So it was convenient, and I chose it, but that 1, 4 matched up with the 2, 1. So if I didn't have the same number of elements in those cases, they wouldn't have matched up. So that's the first thing. If I can say that this guy is an m by n matrix, and then this is an n by r matrix, that's B, what can we say? So what I just wrote here describes that phenomenon. The number of columns here has to equal the number of rows there. Otherwise it won't match up. Okay, and then what are we going to get as a result? We're going to get the outside numbers. So C is going to be an M by R matrix. And then it'll become more clear when we do some rectangular ones and you see the different values. So first thing here for you to glean from this is that these must match. So whenever you're starting out, you'll have some ones in the book that ask you to do matrix multiplication and you can't do it, so it's sort of a trick question. But you have to make sure that the inside numbers match. And that represents the number of columns here has to equal the number of rows. Okay, and then the result, this is the result, is an M by R. So the outer numbers give you the resulting matrix. You can't really see this happen in the 2 by 2 case, but we still have to start with a 2 by 2 because it's the easiest one. So everything's a 2 there, so you can't, these match up and then those also match up, but that's why you get a 2 by 2. It's because of the outer numbers, not because of the inner numbers. Okay, so that's the general setup for multiplication of matrices. First you have to have that situation, then you have to learn how to execute it. So we have to practice executing it a little bit. So let's have some bigger matrices here. Those are the ones I want. Okay, so we got A and B here. We're going to multiply these. And this guy here is a 2 by 3, and this is a 3 by 2. So if I were to do A, B, then that's going to, I know I can do A, B because the 3's match up. And I know that the result of doing that is going to be a 2 by 2. Let's write out one more step here just so you have it for your notes. So it's a 2 by 3 times a 3 by 2, and then those match, and then the result is the outer numbers, 2 by 2. Okay, so let's get started. So if this is going to be C, that's going to be a 2 by 2. Again, I'm going to have a C11, a C12, C21, C22. Those are the entries. I have to find those 4 entries. We're going to do them exactly the same way we did those. Except now we have larger matrices. We have a little bit more to do. So C11, that's going to correspond to, again, if you like the help with the picture, that's going to be the first row with the first column. And I'm not going to write the numbers in this time. I'll just show the image. It's the first row in the first column. Okay, so when I do that, what do I want to do? I'm going to take this row or this column here, and I'm going to turn it on its side, and I'm going to match it up. So I'll get a -1, 2, -3. When you get better at this, you don't have to actually write it down. But at first, if you're not comfortable, you better write it down just to match it up. Okay, so C11 is going to be, I'm going to multiply these two guys. I'm just going to do the multiplication though. Okay, so it's -2 minus 2 minus 9. This is -13. And check my arithmetic here. Let's go to the next board. Okay, C2 or C. Now, when you use this first column, go ahead and use it again on the second one. So that's why I do C11 and then C21. So that way I use the first column in both cases. So we'll do C21. That's going to be the first column again with the second row. C21. Okay, so you see I matched them up there. It's -1, 2, 2, -1. So now I'm going to go -1 in the bottom one. So that's -1. And then 2 times 0, that's 0. And then -3 times -2 is 6. So that gives me a 5. Please ask if you're not sure how I'm getting these numbers. I'm going to reproduce A here, just so I have it. I don't have to pull that board down again. Okay, so now we're moving on. We're going to do C12. So that's going to correspond to the second column with the first row. And I'm going to match up. So now I take the second column over there. That's 0, 1, -2. And I match it up right here with these rows. So 0, 1, -2. And now I'm going to go 0 times 2 is 0. And then I'm going to do 1 times -1. That's -1. And then I'm going to do -2 times 3. That's -6. So I get -7. And then the last one is the C22. That's going to correspond to the second column and the second row. Okay, so now I'll match up the 0 with the 1. That gives me 0. And then 1 with 0. That's 0. And then -2 with -2, that's +4. So that's +4. Okay, so now I can say that AB is equal to -13, 5, -7, 4. When you're first learning it, it might be helpful to do these things, but I think you guys can all appreciate that it's a little tedious, so you want to try to drop it. You also want to try to drop doing this every time, but you need to do whatever it takes to get it right. So if that helps, do that until you're more comfortable, but eventually you want to try to just look at it and kind of do that arithmetic in your head. That'll save a lot of time. Any questions about how I got some of those entries? Yeah.
This is just a general question. I don't know if it's just me, but what do those numbers in the matrix actually mean? Like, do you have, could you graph them, or?
Yeah, we're going to get to that. Yeah, they do actually have meaning. I was alluding to that earlier, that there's some geometry going on behind here. There's parallelograms and areas of parallelograms. So we need to spend a little more time just doing this rudimentary stuff. Eventually I'll start to show you some of that stuff. All right, so so let's turn this on its head. Now we're going to do a little bit more of an advanced one, but I'm not going to write out all the different steps because it just gets a little ridiculous, especially when, if I switch the order here and we now do BA, okay, so BA, that's now going to be, B is a 3 by 2, and A is a 2 by 3. So, okay, I can do that multiplication because they match, and the result is going to be a 3 by 3. So that's got 9 entries, and I don't want to sit there and write out all the 9 entries. So hopefully we've watched it a little bit so we can kind of see the method. Now we'll practice it here with a larger matrix. So I've got to have 9 entries here. If you like, we can write them in. I mean, it's C11, C12, C13, C21, C22, C23, C31, C32, C33. And I don't want, right, we have to get a little bit of a better method for this, so I don't want to have to write out each one of those 9 things. Okay, so let's write them out next to each other. So B is -1, 0, 2, 1, -3, -2. And then A is this, 2, -1, 3, 1, 0, -2. Okay, so what was our method? Our method was take a column and then turn it on its side. And then what we're going to do is we're going to take that and hit each one of those rows. And that's going to give us our first 3 entries. Because that'll be, see, all these have column 1, right? So when I do column 1, I get C11, C21, C23. Those 3 entries come from that. Okay, so let's do that. When I do 2 times -1, that's -2 plus 0. So that's the first entry, -2. Now I'm going to move on to the next row. 2 times 2 is 4, plus 1 times 1 is 5. And then let's move on to the next row. 2 times -3 is -6, plus 1 times -2. So it's -6 minus 2 is -8. So go ahead and stare at that for a second, see if you believe it. See if you wonder how we get it. Okay, we've done everything we can with the first column. Move on to the next column. Next column is -1, 0. Okay, I'm just going to do exactly the same thing. Match those up. That's 1 plus 0. That gives me my first entry here, 1. Then I do -2 plus 0, so -2. Then I do, this is +3 because it's -1 times -3, +3 plus 0. That gives me the second column. Anybody ready to riot in the streets? You all right? Okay. All right, we've done everything we can for the second column. Let's do the third column. It's very methodical. You know, really, I think the main thing you learn here is concentration. This is a way to develop your concentration. I mean, because it takes a lot. Look, I've already gotten distracted. Oh, look, a butterfly. It's hard, right? It's just a bunch of numbers. Okay, so 3, -2, let's go. It's 3 times -1, and then -2 times 0, so that gives me -3. Then I've got 3 times 2 is 6, plus -2, so that's 4. And I've got 3 times -3 is -9, plus 4, so -5. That's BA. Now there's a richness to the multiplication of matrices that you don't get when you multiply 1 by 1 matrices, which are just numbers. So notice, if you have 2 times 3, that's equal to 3 times 2. So when you're just dealing with numbers, you're used to that. You can just multiply them however I want. But look, here we had AB is not equal to BA. So when you move to the matrix world, from the number world, it's a little bit of an extension in the sense that we can do a lot of the same operations. We're going to do addition and multiplication. We're going to learn how to do division. But some of the properties that happen in the numbers don't translate into matrices. Namely, this multiplication is not commutative, right? That's the word we use. If I want to use a fancy math word to describe this, this is not non-commutative. Whereas the real numbers are commutative. It doesn't matter how you multiply them. And you get used to this. So this is a weird thing. Not only are they not equal, I mean, they're not even close, right? This one was a 2 by 2 and this was a 3 by 3. It's just two different animals completely. So that's a little bit interesting. We're going to play around with that a little bit. Let's try to write down the process of multiplication of matrices in general. And then we'll do some special cases and then we'll move on. Let's try to write down the process. So in your mind, try to think about how would you write down this process? How would you describe it, right? The alien comes down and says, gee, I've been watching you from above doing this matrix multiplication. What's the process? Can you describe it in general? Okay, well, first of all, we've got to have something in there that describes the orders, because we had to have a specific thing happen with the orders in order to even do multiplication. So here's your definition. A, B is equal to C if A equals m by n and B equals n by r. And so this is just notation here. What am I really saying? We got this great little thing, i.e. You've seen i.e. before? i.e. is another way of saying another way of saying. So another way of saying this is the number of columns of A is equal to the number of rows of B. That's our starting point. You cannot multiply matrices unless that happens, because that little multiplication won't line up. So that's what I mean by that symbolism there. And let's draw it out. Let's draw out. So here's here's A, and then here's B, and then here's C. This is C here, and so this is a particular element in here, Cij. It's in the ith row and the jth column. That's where it is. So how do I get to that guy? Well, how do we do it, right? We got a couple examples here. So now if I had 1, 2, I took the first row and the second column. So what do I do here? I need the ith row. Let's put some little symbols in here to guide us. I have a little X, a little dot, and a little square. So there's the ith. I'm not specifying. I'm just saying some row in there. It's the ith row. And then over here I've got a column that I'm going to use, the jth column. You see how I'm doing this in general? I'm doing all matrices in the universe simultaneously. It's pretty powerful. Well, okay, so then what am I going to do to match them up? I got entries here, right? And so how do I get Cij? Cij is equal to, well, it's x times x plus dot times dot plus square times square. Now let's try to write that out in English. So it's easy. See, you see the power of the brain? The brain likes visual things. If I tell you that that's the method, you can follow that with your mind, and you get it really quickly. Now, let's let's describe it in words, and let's compare the two. See how your brain deals with describing it in words. Cij is formed how is it formed? Okay, let's write it out. What am I going to do? I'm going to multiply the elements of the ith row with the elements of the jth column, and then I'm going to add them. That's what I'm going to do. So I'm going to write that down. Formed by multiplying the elements of the ith row, but it's not just any ith row, it's the ith row of A. And then what do? I multiply that with the jth column of B, and then I add the results. Now it'd be good for you to sit there and stare at those two things and see if you can read those words. See, what happens is, if you just scan your eyes over this and you read it like a novel, it doesn't register anything. You just go, okay, yeah, Cij is formed by multiplying the elements of the ith row of A by the jth column of B and add the results. Got it? No, that's not the way the brain works. So if you really want to understand math when you're reading it, you really have to dissect it carefully. You have to go through each little word and really understand each word. Otherwise, you can't just read this like a novel. But this here describes that, and that's pretty clear. You can see what's happening. And then you also throw in some examples that we've done, and you can learn this method. You can download it. All right, let's practice on some fancier ones. I got some trickier ones. This one always throws people off. And yet they're simple. So that's why they're good. Okay, so you should try this yourself. So A is, now what do we call that? We call it a row vector. It's a matrix, but it's a specific kind of matrix. It's called a row vector, three-dimensional. And then B, this is going to be a column vector. And now let's do AB and BA, just like we did before. But it's a little harder to deal with this because we don't have clear rows and columns because they only have one entry in them. So let's see if we can follow our method on this one. That'd be good practice. All right, let's start off with AB. Let's go slowly. So A times B, let's just take care of the order. What should we expect? A is a 1 by 3, and B is a 3 by 1, so I'm expecting a 1 by 1. Okay, what's a 1 by 1? It's just a number. Okay, so I'm expecting a real number as a result of that. Now that should be surprising. Why should it be that when I multiply those two that I get a real number? That's the way the matrix multiplication works. Okay, let's do it. Or what do I do? Okay, well, let's just slow down. What do? We take, I know this is going to be a 1 by 1, so there's only one entry, right? C11. And I'm going to take the single column over here and the single row there, and I'm going to match them up. So let's take this on its side, just like we did before, 2, 1, negative 1. Match up those two numbers. So it'll be 2 times 3. Here, I'll write them out again, just so you see it. And then it's 1 times 1 plus negative 1 times 2. And then add all that up. That's 6 plus 1 is 7 minus 2 is 5. So we could call it for just a split second, we can call it a matrix of 1 by 1, but that's not how we write those. It's just 5. Okay, what about the other way? How about BA? Well, all right, in this case, B is a 3 by 1, and A is a 1 by 3, so it's fine to multiply them because the inner numbers match, but the result is going to be a 3 by 3. So I've got this giant matrix that I'm going to get. It's got 9 entries. So let's do that. But look, I've got this little space here. See if I can still get it done. All right. So now I need to have B on the left side. And I need to have A on the right. I know in advance it's going to be a 3 by 3. So I got 9 entries. All right, let's pay attention to what the method was. How am I going to get the C11? I'm going to do the first column. See here, the column's not very interesting. It's just a single number. I'm going to take it and I'm going to turn it on its side, put it over here and match it up. There's only one thing to match up. So it's actually pretty easy to do. It's 3 times 2. There's nothing to add, right? It's 3 times 2 plus nothing else. So I get 6. Then 3 times 1 is 3. 3 times negative 1 is negative 3. Okay, I'm done with that column. I move on to the 1. I get 1 times 2 is 2. 1 times 1 is 1. 1 times negative 1 is negative 1. Done everything I can with that column. Move on. Third column. 2 times 2 is 4. 2 times 1 is 2. 2 times negative 1 is negative 2. You guys with me or against me? Following everything? Any questions? Okay, just a quick thing just to remind you of this, the fact that the multiplication isn't commutative. I have another little example to just practice on now that we're a little more familiar with it. So here's A, and here's B. Now question, how would I get B from A? Let's say I know how I did it, but so there's A, and then there's B. So what have I done to get B from A? See if you see it. I'll tell you, so you don't have to answer it, but can you see what happened? What happened? How do you say it in English? The rows became the columns, right? The rows of A became the columns of B. So that's going to be a move that we do with matrices in a minute. I'll tell you about that in a second, but there's your first exposure to it. What I want to do here first is just multiply these two. We'll do it quickly. Okay, so let me just show you how I would think about that, how quickly I do this. In my mind, I take the 1, 2, and I just match it up with the 1, 2. And so I see that's 1 plus 4 is 5. And then I take the 1, 2, and I match it up here in my mind. So it's negative 1 plus 2 is 1. Okay, now I've done everything I can with that first column. Now I'm going to do the second column. I turn it in my mind. I match that negative 1 up with the 1 and the 1 with the 2. So that's negative 1 plus 2 is also 1. And then I'm not done with the second column. I'll take that, match it up with the negative 1 gets matched with the negative 1. That's 1. And then 1 times 1, so 2. So that's AB. Okay, how about BA? See, the thing is about these 2 by 2 matrices is no matter what, you get a 2 by 2 matrix. So it's possible that you might think that AB is equal to BA in this particular case, because in the rectangular case it's obvious. One time you get a 1 by 1 and the other way you get a 3 by 3. That's clear that they're not equal. Here, let's see that they're still not equal even when we have the dimensions the same. Okay, good time to practice BA. Can you put A on the right side and see that? So what I'm going to do when I do this is I'm going to take this column and I'm going to match it up right here. That's BA. So I'll write it out though. So let's just put it here for a second. 1, 2, negative 1, 1. Okay, so I'm taking that column, but it's good practice for your brain to try to not do that and see if you can still do the multiplication. Okay, so I'm taking that 1, negative 1 and turning it on its side. I have 1 plus 1 is 2. Already they're not equal. It's over. I don't even need to continue. I know they're not equal. We will continue just for practice though. Then I get 2 minus 1 is 1. I'm done with that column. Move on to this column. I get 2 minus 1 is 1. And then 2 times 2 is 4, plus 1 is 5. I really recommend you practice this enough where you can do that in your mind rather than have to write everything out. Just get comfortable with it, get fast at it. So what this is meant to illustrate is that AB is not equal to BA. However, as was mentioned by one of you and also by myself, there's stuff going on inside the matrix that is preserved. So what will happen is the geometry inside this one will be the same as the geometry inside this one. So there is stuff that's preserved when we multiply, and it doesn't matter what way we do it. However, we're not in a position to see that yet. We need to do some more things first. Okay, so that was matrix operations. Okay, now we're on to section 8.3. 8.3 and 8.4 are real short, so we'll get through those pretty quickly. Okay, section 8.3, this is about what's called matrix transposition. So let me ask you, in the English language, if I take a word and I switch 2 letters, what's it called? I take a word, misspelling. Not necessarily. We could come up with an example where you switch them. Probably be okay. Huh? What's it called though? When you switch 2 letters in a word, or even a number if you switch 2 letters. I mean, if you switch 2 of the numbers. It's called a transposition. That's what it's called in English. You look that up in the dictionary. A transposition is just switching. It's moving the position, right, between 2 things. Okay, so now that you know what that is in English, a transposition is just switching 2 letters. What in the matrix could we switch? What do we have available to switch? Yeah, the rows and the columns, just like I did there. Yeah, you switch the rows and the columns. And also, you can think of that in terms of the subscript. So the AIJ is going to be switched, and now it's going to become AJI. That's the transposition. I'll show you that. I'll write all that out in a second. Let's have an example first so we just see what's going on here. If I have A is 1, 2, 3, 4, 5, 6, then the notation we use for A transpose, we're going to use a little exponent. A transpose, that's the notation. So A transpose, it's what I said. We're going to switch the rows and the columns. Okay, so I see this row. That's 1, 2, 3. That's now going to become the first column. And then I see this row. That's now going to become the second column. And then the way we say this, we don't say, you could say it's a transposition of A, but we shorten that and we call this A transpose. That's the way you say it in English, A transpose. So it's just a notation. It's like, with math notation, it's always confusing, right? If you take some of this stuff and you show it to your grandmother, right? If you show this to your grandmother, it's impressive, right? Because math it's got all this fancy notation. Nobody has any idea what it means when they look at it. It just looks really impressive. The way you want to think of math notation is just a shorthand. Because I don't feel like writing out. If I want to tell you I want to switch the rows and the columns, I don't want to have to write out, okay, now take the row and make it the column. I want to just have a symbol that means that. And that's the origin of math notation. It's just we're lazy. That's all it is. So what you want to think of is this is like an icon on your desktop. If you double click it, it's got all kinds of information that pops out. If I hover over it, right, it says A transpose. Or if I hover over it, it says switch the rows and columns. Or if I double click on it, it might have an example or something. So notation is really a convenience. You shouldn't be intimidated by it. I mean, it's hard not to be, but it always think of just double clicking on it. What does it mean? That's how you can start to deal with notation. It's just an icon on your desktop, and it's got extra meaning behind it. Okay, so what we've got here is that the transpose, that implies that the rows of A become the columns of A transpose. That's the easiest way to think about it. And we can have a little visual. If I have A, and here's the columns of A, then A transpose will be this. That's A transpose. And then we can say this a little bit more mathematically. You can say given A with, let's write the order of A. A is m by n with entries. Well, what are the entries of A? I have to write them all down simultaneously. That's A, I, J. That's how we write them all down. And then I and J are, I goes from 1 to m and J goes from 1 to n. Then A transpose. What should A transpose? Now you can really see the word transpose here. You see if it's n by n, then A transpose is m by m. We transpose the dimensions. And here we can also see it with entries. What are the entries? A, J, I. I switch them. See, what happens in math is we define something and then we start thinking about it and we realize there's all these other things we can say about it. So there's the properties of transpose. Well, we notice that if I were to do the transpose of something and then do it again, what should happen? Just look at it in terms of this. If I do the transpose, it becomes n by m, and then I do it again, it goes back to m by n. We just get right back to the same matrix again. We can write that down in symbols like that. And this is just an opportunity to get practice with the symbology and getting comfortable with looking at notation. So there's your first, we can have an example with 1, 2, 3, 4, 5, 6. Okay, if I do the transpose of that, that's 1, 4, 2, 5, 3, 6. And then if I were to do the transpose again, so I do the transpose and then the transpose. Well, on the first one, when I do it, it's this one. And then I do the transpose again, and I get right back to what I started with. This is A, transpose, transpose. Okay, also, if I were to add two matrices and then take the transpose. So imagine I add these two, I get a matrix, then I take the transpose. That's the same as if I took the transpose of the individual matrices. I'm not going to do an example of that, but you could practice that one if you want. You can do the same one there. Do A and B. Okay, and then this one here we're going to play with a little bit. So multiplication, you can just think of it as you kind of distribute the t. It's not exactly that, but you can think of it that way. You distribute the t, so it's AT, BT. So then if I were to follow, if I went up to you and said, this is true, what's this? Stick them up, right? This is, what's this? Then your natural instinct would be to say this is AT, BT, right? But you'd be wrong. So that's why math is kind of interesting. It's not always predictable. This is equal to B transpose A transpose. So let's even just see, so let's have a little, A is 1, 2, 1, negative 1, 3, 0, and B is negative 1, 3, 0, 2, 1, 2. It's a chance to do some quick multiplication here. So A, B, transpose. So first, what that notation means, right? If I double click on this or hover over it, a little window shows up that says multiply AB first, then take the transpose. All right, so let's do that. I'm going to do this multiplication. I'm going to get I can tell right now I'm going to get a 2 by 2 matrix. Okay, let's do this multiplication. I've got negative 1 plus 0 plus 1. So that's 0. Then I've got 1 plus 0 plus 0. That's 1 there. Then I've got 3 plus 4 plus 2. 3 plus 4 plus 2 is 9. Then I've got negative 3 plus 6. Negative 3 plus 6 is positive 3 plus 0. And then now I take the transpose. So that means the rows become the columns, or the columns become the rows, either way. So there's the result of doing AB transpose. And then if I do B transpose A transpose, first let's look at A transpose B transpose. Let's look at that. What would that be? The A transpose would be a 3 by 2. And B transpose is a 2 by 3. So this would be a 3 by 3, right? So this cannot be equal to this because it's 2 by 2. So right away you see there's something fishy going on. If you were to guess A transpose B transpose is this, it wouldn't work out. I'd get a 3 by 3 and over here I get a 2 by 2. So the real result is I have to switch the order and then put the transpose in. Okay, so let's practice that. B transpose it's flatter like this one. So I get negative 1, 0, 1, 3, 2, 2 times A transpose is 1, 2, 1, negative 1, 3, 0. And so now that'll be a 2 by 2. See, I have a 2 by 3 and a 3 by 2 here. So I'll get a 2 by 2, and it's going to be equal to this one. Okay, so let's do this multiplication. I have 1 times negative 1 is negative 1, plus 0 plus 1. That gives me 0. And I get 3 plus 4 plus 2 is 9. Now I move on to this column. Positive 1 plus 0 plus 0. And then I have negative 3 plus 6. Negative 3 plus 6 is positive 3 plus 0. Okay, so that's just an example to believe that statement. And this is our first theorem. This is theorem, well, these are theorems too, but this is the first one I'm going to emphasize. This is theorem 8.4 in the book. And so for my next trick, and your trick too, we're going to do a proof. It's everybody's favorite pastime, writing proofs. But I'm going to hold your hand and walk you through it. It'll be okay. And just so you don't think, okay, well, I'm just going to go to sleep because this will never be on the exam, I actually put this proof on the midterm the last time I taught this class. So if you think this isn't going to show up, it will. Okay, but it's not as bad as you think. It's much worse. No, it's not bad. And you know, all I'm doing here, we're going to do 3 proofs in this class. This is the first one. The other ones will come a little later. And the reason I do that is just because I want to take away the mystery. Okay, you guys are actually going to be able to write proofs. These are the simplest proofs we can come up with, so you can learn them. All right. So the idea of this is, first of all, just to understand what the method of a proof is. What should we be trying to do? So here's what we're going to do. We're going to prove that this is equal to C transpose B transpose A transpose. Okay, so first of all, look back here. It's just an extension of this. This one says if I have A and B and I do transpose, I switch the order and I put a T on each one. This one says if I have A, B, and C, I switch the order and I put a T. So it's believable because we have that one there, if you believe that. So it's at least believable. Okay, now how do you write a proof? So here's the command. Prove this. That's your command. Okay, so how do you write a proof? First of all, you always take a deep breath. And you just say, okay, I'm going to write a proof now. I can't believe I'm about to write a proof. What I have to do is I have to start with this, and then I have to have a logical series of progressions, and then the last thing I write is that. Okay, so let's go. I got to start with this. Here's my proof. A, B, C, transpose. I have to say this equals something to get going. And I know this fact. I know this theorem. I want to use that theorem to get this new result. This is what we do in math. Well, okay, this says something about 3 things, and the only thing I know is something about 2 things. So this is the first step. This is why somebody has to show this to you, because if you don't write proofs, you won't even know where to start. Okay, so what's the starting point? The starting point is, since I know something about 2 matrices, I'm going to just manipulate this and make it look like 2 matrices. Here's my first step. I'm just going to write A, B, C. Can we agree that those are the same? Okay, if I'm going to multiply 3 matrices, I might as well just multiply those first. That gives me a matrix. And then I multiply by C. Okay, but now I'm in the setting where I have one matrix times another matrix transpose. So I can use that theorem now. This is equal to C transpose times A, B transpose. And when I do this step, I need to justify it. The justification is theorem 8.4. Okay, but what's really going on, if you don't like to memorize theorems and their numbers and everything, what's really going on is I'm using the fact that AB transpose equals B transpose A transpose. I'm just using that fact on that specific setup. Okay, but look, can't I do the same thing here? Right, you don't have a fact that says AB transpose equals B transpose A transpose? So now I have one more step here. This is equal to C transpose B transpose A transpose. Again, because AB transpose equals B transpose A transpose. See, I justified my step. And look, I started with that. I had a logical series of progressions where I justified each step. And I arrived at the last conclusion. So we're done. That's it. Done. You could write QED. Maybe you remember that from your geometry class. There's a proof. Okay, so how do you learn to write that proof? You just take a clean piece of paper and you sit there until you can go from the beginning to the end without looking at the clean piece of paper. And if you call it memorization, that's fine. You can call it memorization. I think what will happen is it'll be a little bit of a hybrid between memorization. Did I just put that up and then put it down? It's a hybrid between memorization and actually learning the steps. I mean, if you're really memorizing it, what are you going to do? You're going to go, okay, I start with left open parentheses, A, capital B, capital C, right close parentheses, then little t up above, then left parentheses, oh wait, no, 2 horizontal lines. We got 2 horizontal lines. Then, right, you can memorize it that way, but that's ridiculous. So try to do a combination of memorizing and understanding it. Yeah.
On the test, if we are given a problem like this, for the explanations for each step, can we just write theorem 8.4?
Yeah, because I'll know what it is. Yeah. Yeah, it's fine. That's why I put both there. If you don't like to memorize it, then you write down what the thing, the rule is that you're using. All right, we're almost done. I got just this right here, and we'll be done. Okay. This is section 8.4. Section 8.4 is about, well, it's actually special matrices. And there's just one special matrix we want to talk about, and they're called idempotent matrices. Now, I must confess I don't know the word idempotent. I do see potent, and I kind of think of item as idle. It's kind of like impotent, really. So we'll see why. Okay. So, all right. So let me just give you the definition. If you have matrix A, first of all, it has to be square. So when I say n by n, I could say the word square. I could say n by n. So you're supposed to think of square in your mind when I write that symbolism. And then it has this special property that a squared equals a. Now I had to have n by n in order to even multiply it by itself, because if I do n by n, this is a times a. So this is n by n and n by n. So I'd have to, in order to square it, I had to have those two equal. So you can only square a square matrix. Okay, so it's got this property. Now, let's just look back at the 1 by 1 case, because after all, it's square. So what are the numbers in this case? That would be like saying a squared equals a. Now, I use little a because we're talking about numbers here, not really matrices. And so we can solve this equation. This is a squared minus a equals 0. A times a minus 1 equals 0. So a equals 0. And a equals 1. And that makes sense, right? Those are the only numbers where if you square them, you get the number back again. So that's the 1 by 1 case. Well, in the let's just go to 2 by 2. For instance, just we don't really need to do, we could do 3 by 3, but we'll start with 2 by 2. So for a 2 by 2, we're still going to have this case. Look, if A is 0, 0, 0, 0, then A squared is equal to A. So that's directly, so here's this is the 1 by 1 matrix with 0 everywhere. This is the 2 by 2 matrix with 0 everywhere. This, by the way, is called the null matrix, or the 0 matrix. That's idempotent. It's got that property. Well, how about the 1? What's the equivalent of a 1? Remember that A equals 1, that's like a 1 by 1 matrix with a 1 in there. So that's a diagonal matrix. So we could also have the 2 by 2 where A is equal to the identity. That's an idempotent matrix. Let's see that. A squared, that's equal to 1, 0, 0, 1 times 1, 0, 0, 1. So I'm going to do that on its side. That gives me 1 plus 0. And then do this one. That's 0 plus 0. And then this one is 0 plus 0 as well. And then the last one is 0 plus 1. So there's another idempotent matrix. But the list goes on from there, because in the 1 by 1 case, it was just simple. We could solve that equation. Here, it's much richer. We can have matrices that when you square them, they give you themselves back again, but they don't look anything like this. So let's have another example of that. It'd be kind of challenging to go try to find some idempotent matrices. Try to find the formula that gives you all the idempotent matrices. Okay, so let's check that out. At first glance, you wouldn't expect it to be. It's got too many things that are, kind of bigger numbers. So I wouldn't expect to get that back again, but you do. So 3, negative 3, 2, negative 2 times 3, negative 3, 2, negative 2. Okay, I'm going to take this and put it on its side. That's 3 times 3 is 9, minus 6 is 3. And then 6 minus 4 is 2. Now, these are negatives here. They aren't just tick marks on the board. Then I have negative 3 plus 6 is negative 3. And then the last one, I have negative 6 plus 4 is negative 2. So there's an idempotent matrix. A trace of a matrix. This is the last concept from section 8.4. This is an easy thing to compute, but if nobody tells you what it is and you have no idea what to do. So this trace here, this has a word. So think about what trace might mean. I think of a couple things. You could trace something where you put a transparent piece of paper and you trace something. But you can also think of trace elements. And that's really what's going on here. The trace of a matrix, there's this, if you boil it down, the residue of the matrix, the sort of essence of it, is found partly in the trace. And we're not going to be able to see that for a while, but I can still tell you what it is. Okay, so A, let's see if you can guess it. I'm going to tell you that the trace of A, that's the notation for it, trace A. I'll tell you that that's 8. So how would you get 8 from that configuration? How about 3 plus 5, right? So the trace is the sum of the elements of what? What's the vocabulary? It's the main diagonal. So it's a very easy thing to compute. You just have to know what it is to compute. And we'll just have one more example and that's it. So I've got a 4 by 4 matrix, and the trace of A, well, it's just going to be, no matter how complicated it is, I just take the main diagonal and add up those elements. So we got 27, 33, 34. That's an easy thing to compute. Okay, that's the end of section 8.4. We'll start on 9.1 on Monday. Enjoy your weekend.